question was about the limit properties. And what I want you to do is, we don't know that this is symmetric. So I cannot say that f of negative x, okay, is equal to a negative of f of x, okay? If that was the case, then I would know that this was an odd function. I'm not given that information. That's only true when f of x is an odd function. However, I can take the sign and take it out. So I'm going to change this limit and I'm going to break it up. So I'm going to say the limit as x goes to negative 5 of f of x plus 3 times the limit as x goes to 5 of g of x. So I have those specific limits. Here's the first one. So I know this value is 4 plus 3 times the limit is g of g as it goes to 5 is also 5. And so this is going to give me the value of 19, okay? Now, a couple of you gave me an answer of 13 because you pulled the 2, okay? Or you gave me 17 instead. That's, you know, if you showed me the work, I took off only 1 point instead of 2. That's the whole idea. I get my students doing this a lot so I can show them where they made the error in their reasoning. And therefore, if you show me some progress in here, I don't have to take all the full credit off. And they really, really like that. Sometimes if it's just even a sign error, I'll take off a half a point. Okay? We all make sign errors. I make sign errors. Everybody makes sign errors. I gave back quizzes this week, and I had at least 4 people in class on one quiz, or they had 2 quizzes, or the other that made a sign error. And it happens. It's real life. Okay, that's it. So this one, we're doing the graph of f that's shown here. Okay, make sure you always read to see where the graph belongs to the question. So we're looking at the limit as x goes to 0. So what I want to do first is say, what is the limit as x goes to 0 of 1 minus x squared? So I'm looking as x goes to 0. I'm looking as it approaches this way. Oh, sorry, I went over it. Let me change this. Yep, I think I got it down here. As it's approaching 0 from the left and 0 from the right, that's actually going to 2. So what we have here, let me actually make this a little bit bigger. There we go. So this is going to be 1 minus 0, okay? And this is going to give me 1 from above, okay? So I want to say, actually, no, I want to do 1 from the below because the graph actually happens to be below in here. So this is 0, but 0 from above. So we're approaching 0 from above the point. So I'm going to write 0 with a plus as a superscript. And that means my answer is going to be 1 with a negative, okay? So, because I'm subtracting numbers going into that. Now, now I want to look at what's the limit as x is approaching 1 from the left. So I will take this answer and put it into my new limit of f of x. And 1 from the left is going to 3. So that's looking at, let's put a little orange in here. As I'm approaching this guy right here, I'm approaching 3. It's not asking me what is, remember, this is not the same as saying, what is f of 1, which happens to be 2. These are not the same thing. Okay. And as I'm going through these, if you have questions, it's hard for me to see the chat because I actually don't have I forgot to bring a second laptop home this weekend. So please just turn on your sound and just ask me questions. Okay. I have no problem answering questions. So I get peppered with questions all day long. All right. So that was actually looking at this answer. And then this one, you actually had to go through each one of them to look at this. And you're looking for the one that is false. Okay, and that happens to be C in here. And the reason why is because the limit does exist, but you have to break it up and do the limit from the left and the limit from the right. So I'm going to look at what's the limit as x goes to 1 from the left of f of x, times the limit as x goes to 1 from the left of g of x plus 1. Okay, so what I'm going to do is modify this just a little bit. So if f of x as x approaches 1 from the left, I'm going to do that in green. That's going to 0. That's going to be great. So this is going to be 0. Whoop, not in highlighter. Do this in green. Times. Now, what I'm going to have here is, what is the limit now as x approaches, okay? So if I put in 1, as I'm approaching 1 from the left of x plus 1. So that's asking me, what do I get as I'm approaching here? And I'm looking at, that would be the limit as it goes to 2. So from the left, and that's going to be a 1. So let me actually take this out and make this 1, and therefore this is 0. Now do the same thing from the right. So I'm going to throw that in a different color. What's the limit as x approaches 1 from the right of f of x times the limit as x approaches 1 from the right of g of x plus 1. Okay, so as I approach 1 from the right, so I'm going to do this, I'm going to throw some, good gracious, can I have like a little bit more color? Let's throw, whoa, all kinds of colors in here. Let's see, let's make it darker pink. So here we go. We're approaching 1 from the right, okay? And that's going to 0. It's going to 0 from below. So I can actually write 0 minus if I want, okay? But that's going to be 0. As I'm approaching 1 from the right, that means I'm approaching 2. And that is here, and that's going to -1. So I'm going to toss in a -1 here, but this gives me 0. So this limit is actually going to 0 because the limit from the left is equal to the limit from the right. So I can say the limit as x goes to 1 of f of x times g of x plus 1 happens to be 0. So anytime you see this, we're doing like a multiplication or division, we're actually going to break it up into limits from the left and limits from the right, okay? And that's what we're going to be looking at there. So the same thing with D actually does not exist, okay? So this, yeah, that's true. It does exist because we wanted the statement that was false. So this happens to be true. This happens to be true because if I take the limit from the left, as x goes to 2 from the left of g of x, this is 1. If I take the limit as x goes to 2 from the right of g of x, this is -1. So the limit does not exist because they're not the same. The limit as x goes to 1 of f of x, that's 0. So we actually showed that already, okay? Looking at the diagram. And then we had this one. I love this diagram, okay? So we're looking at the limit as x is going to -2. All right, so I'm going to do green because I'm going to do pink because I'm going from the right. So I'm going to try to be consistent. So I'm doing -2, all right, which is actually right here. Let's put this in here. Here's -2 from the right-hand side. And that value happens to be going to -1. Okay, if I look at it, go down to C, okay, it wants -2 from the left. All right, so I'm doing left-hand side. So I see that this is going up to +2. Or is that 2 or is that 3? That's 3. I didn't read it right. Okay, so this happens to be 3. All right, what is then so B is there to throw you off. B did not ask you what is the limit as x goes to -2. It says, what is the limit as x is going to 2? And what I can see is here's 2 right here on the, I hit the yellow, sorry. Come back here. Here's 2 right here on the graph. And so I noticed that the limit from the left and the limit from the right are both going to 3. Okay. And then this one is actually saying, what is it as we're approaching 1 from the left? Okay. So from the left, I'm using green today. So I go up and I see as I'm approaching 1 from the left, this is actually going to 7. You actually have to count it. Somebody said 8, that's fine. And on the last quiz, people had gave me, we just didn't count. I had 6 the first time I did it. So this is 1, 2, 3, 4, 5, 6, 7. So that actually happens to be the answer to this one. Okay. So piecewise functions are really kind of the big way we start talking about left hand and right hand limits. Okay. And then today we're going to be looking at what happens to functions that oscillate, what happens to functions that have undefined domains where we have rational asymptotes, okay? And that's what we're going to be looking at today. So we're going to start with squeeze theorem, and then we're going to look at what happens as the limit goes to infinity, okay? And then hopefully we'll be able to close today with the intermediate value theorem. So I want to take a moment to jump back, come back in here to the notes, okay? And we were looking at, and in fact, one of the things that I recommended on quiz 2, the very first question was a piecewise function. When you have a piecewise function, if you can, graph it, okay? I personally don't care whether you're doing, graphing calculator or Desmos or something. If you're not comfortable graphing it by hand, then graph it in Desmos, okay? So I actually have one up and open for today, for what we're going to be needing in just a couple of minutes for a certain problem, okay? So we're going to look at trig limits today and kind of the analytical approach that happens with them. So we actually are showing them by doing what we call the squeeze theorem. And the squeeze theorem says this: I have two functions, h of x and g of x. And at some point C, h of x and g of x are equal to each other. So notice in this that here, that these are less than or equal to signs. So there was going to be a point where h of x is equal to f of x is equal to g of x. So what we have is, we have a function g of x that lies above the function in the middle. We'll call it f, okay? And then we have another function, h of x, that lies below the two functions. And at some point they come in and they're equal to the same value. We're just going to call that value L, okay? Right here. And so we're going to use that squeeze theorem to actually show that. So we have something, and these are two things that you have to pretty much memorize because they're going to show up everywhere, okay? That the limit as x goes to 0, sine x over x is 1, or you can reciprocate it. So this is the reciprocal, because the reciprocal, flipping 1 is still 1, right? Okay. Also, if you take the limit as x goes to 0, 1 minus cosine x over x, or cosine x minus 1, okay, either way, that goes to 0. Now, we will eventually, trying to think when we do L'Hopital's rule, I think unit 3, okay? I think about that, unit 3 or unit 4. We're going to talk about L'Hopital's rule. So when we take derivatives, we'll actually be able to prove this, okay? But we're going to do it with a geometry proof right now, all right? So we're going to use theta for our angle instead of x because it gets a little confusing when I'm working on the coordinate plane. I want x to be my horizontal value, my y to be my vertical value, okay? So I have a circle, all right? And it's got a unit length of 1. So that's its radius is 1. And I know that any point on the unit circle, the values are cosine comma sine. Okay, that's how we learned it all in pre-calculus. Now, if I take it and I extend out this 1 and I go up, okay, then actually up here I have this point. Let's see, let me put some little color in here. No, it didn't work. There we go, right here. Okay. So if my x is 1, or if I divide by my cosine in both, then I basically get the point 1 and tangent. So this is really taking cosine and dividing both of these by cosine. And that actually kind of will give me this, okay? So if I look at the area of the two triangles and compare to the area of the sector, all right? So the first triangle, the big one that I kind of highlighted with the pink, all right, has the area of 1/2 base times height. Well, if the base is 1, the height is tangent, then tangent over 2 is the area of that triangle, for the larger triangle. If I take the smaller triangle, which is basically, let me draw it in orange here. This is my smaller triangle, okay? And so this has a height of sine, all right? It still has a base of 1. So the area is sine of theta over 2. And that means the area of the sector, remember sector formulas, okay, is actually theta divided by 2. So if we multiply each expression by 2 sine theta, what we get, so we're basically wanting to take this to become 1, okay? Then we get the tangent theta over 2. The 2's will cancel. We'll have tangent divided by sine. That's going to give me 1 over cosine, okay? So if I have tangent theta over 2, and I multiply by 2 over sine of theta. So this is sine over cosine, and then this is sine over 1. Keep, change, flip, you're ending up with 1 over cosine. Then you have theta, and the 2's will cancel again here, because you're going to have theta over 2 times 2 over sine. So that will be this one. Okay, if you reciprocate them, you get that cosine theta is less than or equal to sine theta over theta is less than or equal to 1. Now, if you take the limit as theta goes to 0. So what's the limit as theta goes to 0 of cosine theta? That happens to be 1. So what I have now is 1 is less than or equal to sine theta over theta is less than or equal to 1. So by squeeze theorem, okay, we have shown that the limit as theta goes to 0 of sine theta over theta is actually 1, okay? You can do the same thing for the cosine one. Take my word for it, okay? So what we're going to do now is apply this and see how this works in a few problems. So you're going to have some really fundamental trig manipulations to do. So we're going to change tangent. We're going to rewrite this as sine over cosine. And we're going to divide this by x over 1. So this gives me the limit as x goes to 0 of sine of x. I'm going to flip the x here times 1 over cosine of x. And I'm going to break this function up. That means I can take these limits individually, okay? So I can use my limit rules and say, this is the limit, okay? The limit of the product is the product of the limits. So I can say sine x over x, and I can take the limit as x goes to 0 of 1 over cosine x. Now, we know sine and cosine are very nice continuous functions. So And I know that this value is going to go to 1 because that's what cosine of 0 is. And I know from the other definition that this is also 1. Okay. So I get an answer of 1. If I want to use something like sine 4x in example 2, then I need to also have my denominator has to match my argument. So this has to match this. And in order to make that work, I just multiply by 4 over 4. So I'm going to take the numerator 4 outside of this. And I'm going to take the denominator 4 so that this matches up. So I can say now that this is 4 times 1 because I know that this is what the limit's going to go to. So this answer is 4. Now, in example 3, there's a couple of different ways I can do this. I actually really like the problems with 1 minus cosine squared. The easier thing to do is to replace that with sine squared, because we know that Pythagorean triple, sine squared x plus cosine squared x is equal to 1. So we know that sine squared is 1 minus cosine squared. So coming back into this, I can say the limit as x goes to 0, then I have sine squared x over x. Okay, so what I'm going to do is split my limit up again. And this is going to be sine of x over x. Okay, and I'm going to say the limit as x goes to 0 of the extra sine x. Okay, I know the first one is 1, the second one is 0, so this limit is 0. That's it. Okay, the other thing I can do is I can factor it. So this is we're going to call this like number 1. Okay, number 2 is I can factor this. So I can say the limit as x goes to 0 of 1 minus cosine x, all this over x, and 1 plus cosine x. Okay, so I can break this up again. So this is the limit as x goes to 0, 1 minus cosine x. I'm going to put the x over here, times the limit as x goes to 0 of 1 plus cosine x. Now, the limit on the right is 2, because if I put a 0 in, I'm going to get cosine. So this is going to be cosine. I don't need the limit. I just need to evaluate it. So this is going to be 1 plus cosine of 0. So this will give me 2. Okay. Here, I know that this limit on the left, that's going to go to 0. So I have 0 times 2 and gives me 0. Regardless of the way I do it, I should get the same answer both times. So this one's nice because basically you can come in and check the work. Okay. And that's it. So that's kind of a neat way to approach it. And it also gives you that flexibility that if you can't remember that 1 minus cosine squared is sine squared, factoring is always the way to go. All right. So what we're going to look at now is we're going to show that using the squeeze theorem, okay, that the limit of f of x, given here is x squared cosine 10 times pi x, okay, that goes to 0. And so what we're going to do is we're actually going to use that with the squeeze theorem. So we're going to say, what is the limit as x goes to 0, okay, of negative h, so of h of x is less than or equal to the limit as x goes to 0 of f of x is less than or equal to the limit as x goes to 0 of g of x. Okay, now the easiest way to show this is to do it graphically. All right, but what I know is from the first one, I know that this is going to be 0, okay, because it's negative x squared. So this is going to be negative 0 squared less than or equal to the limit as x goes to 0 of f of x is less than or equal to 0 squared. So I get that the limit here, okay, is 0. So let's graph this. So if I graphed g of x, let's see, let's see, 0.5, this is 0.25. If I have 1, it's 1. I come out here, this is here, -1 is 1. So this is my g of x. Okay. Now, if I take my h of x, it does the same thing, except it's negated. Okay. So it's coming down like this. So here's my h of x. So you can see that it's going to squeeze in. Now, if you graph x squared cosine 10 pi x, okay, it's going to go bonkers on you, and it's going to do this. It does this, and then it comes back out like this. All right. So let's see. Let me write this down. So x squared cosine 10 pi x. Okay. So I'm going to say y equal to x squared. All right. Y equal to a negative x squared. There we go. Okay. And I can move in on this. And then I'm going to say y equal to x squared. And then I'm going to go over cosine 10 pi. If you just type pi, you get that. And look how that guy oscillates. Whoa. It is like crazy. Okay. And it's like one of the coolest functions to look at. Now, if I stretch this out, notice how it gets closer and closer as I'm getting in. It gets closer and closer to 0. Okay, my graph doesn't want to come out anymore. And it just keeps doing that. So it's actually going to come back in here. If I click on it, I will get 0, 0. Okay. Now I'm trying to see if I hit, yep, at 0.5, it gives me 0. It's pretty good. But I really like doing it Desmos. One, I like the color coming in, being able to see everything, so I can see one function versus the other, and I can see how my squeeze theorem is coming into play here. Okay, that's kind of a neat thing. So you have the TI Inspires, okay, that graph in color, you know you can do those in there as well, okay? But since I don't have Inspires, I love Desmos, all right? And that's the thing. So also, if you get really stuck on doing a piecewise function, then if you don't know how to graph a piecewise function in Desmos, let me know. Well, we can certainly definitely do one in here. I have to remember the parentheses to put the boundaries in, okay?